Okay, let's talk about a two-tailed test. This is section 9.1. So the idea here is that we have a hypothesis. In this case, it's going to be a hypothesis about the mean of a population. We'll see the details in a second. And then we have the alternative hypothesis is that the mean is not equal to the hypothesized value. And the way that we test this hypothesis is by collecting some data and see how our data relates to this. In other words, how is the mean of our data close to this or far away from this? If it's close to this, we're going to say that this is true. This is true. If it's far away from this number, then we'll say that this is not true, and we'll adopt the alternative hypothesis. So the details are that there's a magazine that conducted a survey in 2008, and they looked at 6th graders, and they looked at the average weight of their backpacks, and it turned out to be 18.4 pounds. Now another magazine wants to check whether this has changed since that survey. So they're going to take another sample, and they're going to test. So our hypothesis is that it's not changed. That's called the null hypothesis. That is that it's still 18.4, and the alternative hypothesis here is that it's not the same. It's changed. And they write it like this, the null hypothesis, and the alternative hypothesis like that. Now here in our text they go into the details about whether this should be a one-tailed test or a two-tailed test, and we already talked about that, and this is a two-tailed test, so I won't go through that again. So this is the picture of the situation. So the null hypothesis is is the picture that we assume is true. That is, we say that the mean is at 18.4, which was the null hypothesis, and then even though the mean is there, we know that the sampling distribution of x bar, the sampling distribution of the mean, means that sometimes we don't always expect that if we take a sample that we're going to get exactly 18.4. We might get something a bit higher. We might get something a bit lower. So this curve describes the probability that we'll get something lower and that we'll get something higher. Now if we get something really far away from here, like in here, then we're going to say we doubt that this is actually true. So we're going to reject the null hypothesis. So if we get something within this region called the non-rejection region, we won't reject this. But if we get something really far away, either out here or out here, and this is a two-tailed test, so that there's this or this side will cause us to reject, then we will reject. Now just going on for a second, if it was a left-tailed test, we talked about this example, then we would only have one side where we would reject. We wouldn't reject when things are up here. If you read this example, you should understand why we wouldn't reject if things are up here. And then here we're going to go, this is section 9.2, we're going to go into the details about actually the numbers that would cause us to reject or not reject. So just like before, we have different cases depending on the size of the sample and different assumptions. So we use different tables. We use the normal table or the t-table depending on the assumptions and the size of the sample. And here, this is when sigma is known, and then section 9.2 is the more realistic case when sigma is not known. So then we have to use use the t-table, and again we have the cases, case 1, case 2, case 3, and you can check these. These are similar to what we looked at before. But what we have to do is calculate our test statistic and then see how far away that is from the hypothesized mean. Remember, the hypothesized mean in our last example was 18.4 pounds. In other words, here. Here. This is the hypothesized mean. Then we calculate our t statistic, and if it's out in here, we're going to reject. If it's in here, we won't reject. If it's out here, we will reject. So that's here. The calculation that we do, in this case when sigma is not known, is this. We calculate the t statistic like this, and we can use this calculation here. So once you've calculated the test statistic here, if it's in the rejection region, you will reject the null hypothesis. If it's not in the rejection region, you won't reject the null hypothesis. Now there's another approach called the p-value approach. And all that means is we still calculate the test statistic t, and so maybe it turns out to be 2.121. So is that in the rejection region or not? Well, that's one way. That's one question you can ask. But the p-value approach just says, tell me. It doesn't say we don't set up a rejection region here and a rejection region here. We don't bother to do that. It's still, of course, the same calculations, but we don't set up this rejection region. We just calculate the t-value, and then we just ask what is the area in here and here if we're doing a two-tailed test. And you can find that area just by looking at the t-table or the normal table if you're using the normal table, but usually we'll be using the t-table. You just figure out what the area is in here and here. You add them up in the case of two-tailed test. And you just report that value. So normally, like we do a 95% confidence interval. So we would use a 95% rejection region. So in here would be 95% of the area, and out here would be 5%. So if our t-test is out here, then in that case, going back to this example, so if our t-value was here, normally, if we set it up this way with the rejection region, since it falls into the rejection region, we would reject the null hypothesis. But if we don't set up this rejection region sort of beforehand, we just find out what the t-value is. It turns out to be out here. Then the p-value, which you can look up in the t-table, will be less than 5%, right? If the rejection region, the total area was 5%, and we get something out here, then the area to the right of here plus the area to the left of here will be less than 5% because the area from here to here was 5%. So it'll be less than that. So in other words, if the p-value is less than 5%, usually we will reject the null hypothesis if we're doing a 95% test. Okay, so that's the idea. So here's an example. A psychologist claims that the mean age at which children start walking is 12.5 months. Carol wants to check this claim, so she took a sample of 18 children and found that the mean age at which these children started walking was 12.9 months. So the question is, can we reject this hypothesis? And instead of doing it by setting up a rejection acceptance region, we do it with the p-value. So we found that it was 12.9 months. Standard deviation turned out to be this. They said they're assuming that everything is normally distributed. Find the p-value for the test that the mean age at which all children start walking is different than 12.5 months. So let's see. What will your conclusion be if the significance level is 1%? So we do this. Let mu be the mean age at which all children start walking. So our x bar was 12.9. S was 0.8. State the null hypothesis that it's equal to 12.5. The alternative hypothesis that it's not equal to 12.5. Select the distribution to use. I think we're going to use the t distribution. Calculate the p-value. So the sign in the alternative hypothesis is not equal to, so therefore it's a two-tailed test. So to find the p-value, first we find the degrees of freedom and the t-value for 12.9. So degrees of freedom just means what? That the sample was of size 18, so the degrees of freedom is one less than that, so it's 17. So the degrees of freedom is 17, and the x bar was 12.9. So what do? We say the standard deviation of x bar, s sub x bar, is this divided by the square root of 18, sample size. So it turns out to be this. So that's the standard deviation for x bar. Then we can calculate x bar minus mu over that. So that's 12.9 minus the hypothesized value 12.5 divided by this 2.121. Degrees of freedom is 17. We go to the table. It's table 5 in this case because it's the t table. In this row we find it. So you look it up and you find that we have to estimate it's between this one and this one. So the test statistic 2.121 falls between these two values. And so I'm not going to go through the table right now, but I hope you can figure that out. So it turns out that the associated areas are this and this. So the p-value, if you go through these calculations and looking at the table, the p-value turns out to be between 2% and 5%. Basically, that means that we're beyond the rejection region. We don't really use the rejection region, but it's the same thing. We've gone beyond the rejection region, right? Because we're, well, 5% actually may not be beyond the rejection region, except that they said that they want to reject at the 1% level. Didn't they say that? I think they said that. Yeah, at the 1%. So so depending on what alpha is, we're going to end up rejecting or not rejecting. Remember, alpha is the error level. So if the error level was 5%, then we'd probably reject it. It was really clear. It was actually between this and this, so it could actually be, p-value actually might have been 5%, but actually it's not equal to here. So it's less than 5%. So if alpha was set at 5%, our p-value was less than that, so we would reject. But actually our alpha, for this problem, they wanted to do it at the 99%, so alpha is equal to 1%. So in that case, the p-value is not less than this, so we won't reject the claim at the 1% error level. Okay, so that's the idea. So the the smaller the p-value, the more likely we are to reject the hypothesis. But of course you have to say exactly. So if your alpha is, if you're doing a 5% test, then if the p-value is less than 5%, you'll reject. If you're doing a 1% test or 1% error level, then the p-value has to be less than this in order to reject. Okay, so go through some examples here to see how this works. But basically, when the p-value is small, we're more likely to reject the null hypothesis. So you need to remember that rule at least.